Hello all, welcome back to the session. So the agenda and the topics for day today is LLM fundamentals and prompt engineering. So the agenda goes like this. We will learn about LLM basics, working of LLM, the building blocks, tokenization, embedding, two important concepts which are related to LLM, followed by prompt engineering, the core principles of prompt engineering, and various ways of implementing prompt engineering, which is in general terms known as prompt patterns. So we will see prompt patterns from the perspective of normal user, and we'll also implement it using Python code, correct? So both the things we will do. And at the end, we will also have a look at few interview questions pertaining to this topic, which we covered today. So overall, you will have a complete journey from basics to the advanced concepts. It will include a lot of examples, analogies, best practices, and of course, as usual, we will have hands-on Python exercises. Okay. So the first question comes: what are LLM? Correct. So LLM stands for large language models. So these are models which are based upon neural networks. Using neural networks, LLMs are trained on massive amount of textual data. So a large amount of textual data are given and LLMs are trained on it. On this data which is given to them, they apply various patterns, and the output of which is to either generate text or classify a text or summarize a text. So these are the three major use cases. Using the existing data, it can generate new text, new essays. It can classify the contents, and at the same time it can also summarize, correct? Generate a summary from a large text. It's built on an architecture which is known as transformer architecture, and you can imagine LLMs as something which can predict based upon the context, correct? So they have the capability of predicting text based upon the context you set. They form the backbone of agentic AI. Okay, because we use LLMs a lot. If you remember, yesterday also we used LLM for a couple of our examples, correct? So they form the backbone of agentic AI. So how does LLM work? So it takes input text, it divides the input text into tokens. That process is known as tokenization. You can imagine input text as a sentence. It will break the sentence into words. That's what we call as tokenization, which is then passed through neural networks, which will transform this text. Yes, you heard it right. It will transform this text. See, all the machine learning algorithms are algorithms which work on numerical data. So there will be a process in which we will be converting these tokens to a numerical representation. Correct? That process is known as embedding. Now, along with that, it will also do attention. So, in a sentence, you may have words which are supporting words, but which are not very critical. Correct? So, there are certain words which are very significant and important. Such words are known as attention words. So, in a given text, it will try to find out attention words and get the token, and at the same time convert that token to numerical representation, and using a decoder it can predict the next token. Okay, so now one question which might come into your mind is, why don't we convert everything to numerical representation? So one thing you have to remember, in any algorithm, we always consider space and time, correct? So if you land up storing unwanted data, that will slow down the process and also increase the storage, correct? That's why we select only the critical words and we base everything based upon critical words, correct? So that's the way we work. So, so transformer architecture, as I told you, it can have a encoder, it will have a decoder, it will have multi-head attention mechanism. We already learned what is attention. It will try to find out words which are very critical. It will have feed forward layers and residual connections and layer norms, correct? So basically, they will process your input textual data, convert into numerical format. Now, before converting, it will find out words which are very critical, convert them to numerical models or numerical representation, and feed it forward to the output layers so that using this data, they can predict the output, correct? So, that is what the transformer architecture does. Okay. For doing that, it internally makes use of various mathematical formulas, including dot product. So in mathematics, we have heard about dot product between vectors, correct? So that is what it uses internally to calculate, you can say to calculate relationships. Along with that, there is something known as cosine similarity. So if you have two words and if you want to see whether the two words are related, for that internally, after converting the textual data to numeric values, we can make use of cosine similarity, which will give as a result indicating whether there is relationship between two words or not. Okay. So using this all mechanisms, we will be able to LLM makes use of textual data as input and of course generates textual data as output, correct? Now, how many layers of transformers are there depends upon organization and depends upon the complexity of the task. It can have somewhere around 24 to 200 layers as a general example, correct? So, in the LLM, there are three major stages. First is pre-training, then fine tuning, and then instruction tuning, correct? Three steps. So, pre-training means learn from general language patterns. So, why did the AI come recently and not many years? Because even though it was the work on AI started pretty much many years before, is because number one, you have to collect the massive data set, convert that massive data set to computer recognizable format, correct? And secondly, you also had to feed this data to LLM. So you have to pre-train the LLM with this large data. More better the data, the more better will be your LLM, correct? And then you will have to tune it. Now, tuning is required because there might be requirements for a particular domain. So when you come to a domain, certain words have very important meaning as compared to others, correct? So when we go for educational domain, the healthcare domain, as well as financial domain, each domain have a particular way of representing information using text, correct? So they have certain words which are used more on that domain, correct? So you will have to tune, the LLM has to tune itself to adapt to that particular domain. That is what we call as fine tuning. And finally, instruction tuning. Instruction tuning means when a human being gives an input to a model, the model should be able to understand that input and perform operations like rating and also see what type of models can be used to satisfy the request by the corresponding humans, correct? So these are the three stages involved in any LLM: pre-training, fine tuning, and instruction tuning. Okay. So tokenization, as I told you, it takes a text. You can imagine it as a sentence and divides that sentence into tokens. Tokens are like words. For example, playing football can be tokenized as play ing football. Correct? Now, why we have to divide big words into small words? As I told you, out of all these words, only few words will be selected to represent the context. Not all the words will be selected. If you remember, we called it attractive words, correct? So it will make use of attractive words. Now, remember, there is a small difference between tokens and words. Okay. So, playing is a word, while play is a token, correct? So, we cannot map tokens exactly to a word because tokens are further or word can be further divided into tokens. As you can see above, plain, which is a word in English, correct? So, that became play and ing. So, you can imagine tokens as something which is granular, more granular to words. Okay. Same way, the token count, as I told you, why we don't take all the tokens as such, we will have to drop some tokens because of cost and latency. More words you store, more money you will have to pay for storage, and the model will have to work on all that entire words. So naturally, it can become slow. Correct. So there is a cost and latency factor. So we don't take all the counts. Correct. Now there are many tokenizers available which divides a given text to tokens. Correct. So different token split algorithms are available. We can select the algorithm of our choice. Correct. Based upon our needs. So this is what is tokenization. So the takeaway from this is that token is more granular as compared to words. A single word could also be divided to two or more tokens. Correct. That's the takeaway. Now, if you see, we spoke few minutes before. I told you about embedding. Correct. So, what is embedding? Embedding means converting the words and sentences into vectors. We call it. So, vectors are numerical representation of text. Correct. For example, if you see here, king, man plus woman equals queen. So, there is a relationship between king and queen. Correct. So, that relationship is what we call as semantic relationships. So, such relationships can be easily calculated if you use embedding. So, using embedding, you can convert your data or textual data to numerical representation so that various numerical related functions can be applied on it. So, this will be used for clustering. Clustering is grouping of data based upon common behavior. It can also be used for semantic search, and it can also be used for RAG, retrieval augmented generation. Each of this we will see, correct, as we go further. So attention mechanism, I told you, attention mechanism refers to model where to look for in the input sequence, correct? For example, in this sentence, the trophy doesn't fit in the suitcase because it is too big. The attention helps model resolve what it automatically refers to. So when the model will read this sentence, it will automatically come to know it. What is the meaning of it? Correct? It refers to trophy. So this type of attention, it can automatically get, correct? Yes. So for this, it makes use of multiple head pattern and it runs parallelly to identify this contextual information, correct? Now we also have decoding strategies. In the decoding strategies, we make use of various types of algorithms like greedy search algorithm picks the best token in each step. Beam search makes use of the best path rather than selecting tokens, it selects the best path. Temperature 0 means factual, 1 means creativity, correct? So greater than 1 is creativity. So you can control whether the LM should give you factual information or can it also generate informations which are more creative side, correct? Which not be fact which may know which may not be completely factual. Okay. And top case samplings. So how many tokens you want to sample, top P samplings, correct? How much probability you want to select. So these are all things which are used for decoding, correct? Internally. Okay. So that's what LLM has to offer. So using LLM, so what we learned till now is what is LLM, what are the building blocks of LLM, what is embedding, correct? And what significance LLM plays. Okay. So as usual, we will try to do some examples, correct, around that. So what I will do, so you can see this LLM sample one. Okay, so we are making use of Olama. I have already started, so I will need to start Olama in my Docker. So I will open cmd and say Docker start Olama. Great. So Olama server is started. You know, default mall is LLAMA3. Okay, so what we are doing here, we have a function with name send completion. So in send completion, we are making use of prompt. We are making use of a model. We are making use of temperature. Hopefully the meaning is clear. 0, 0 means factual. 1 greater than 1 means more creative rather than being factual. And maximum tokens, correct? You can see maximum tokens are 300. Then when we chat, we give the model, we give the message, we give the content question basically. And we also give these options, correct? What all options we have. And whatever response comes from the corresponding provider, in our case, it's Olama, it gives message and content, correct? So if you see this example, in this example, what we are doing is we are classifying movies, whether the movie reviews, based upon the review, whether the movie is positive or not. So we are giving few examples. Here you can see you are an assistant that classify movies as positive or negative. And you are given examples. Review, I loved the movie. It becomes positive. Boring, too long, unpredictable. This is negative. So you see, you are given label. So you can imagine this as clustering. Based upon the review, you will cluster the response as positive or negative. Now, what you want is you want the model to predict the label based upon the review. So new review will come. Based upon that review, you want to classify whether the output will be either positive or negative. So that's what we are doing in classify review. So what we are doing, we are using review and few short template. This particular text which we created, this is a string. So in Python, this triple quotes is used for creating a string which is very big, correct? So we are saying few short template dot format. Please replace review with the review which I gave and call the above method send completion, correct? In which I pass the prompt temperature equals 0.0 means I want factual data only and maximum tokens equals 10, 20, correct? So now, as an example, review, the plot was amazing and the visuals were stunning. And we call this classify review method. So when I call this classify review, this review text will be passed. And in this, the template which we made, in that template, we will replace the review with this review which we gave. And we call the send completion method, which will actually go and call Olama with this corresponding details which we passed. And based upon the response it gives, we will print the response to the user, correct? So you see here we are using LLM to classify a review. Okay, so if I try to run this, you see this. Let me go to this folder. Just here, here. Again, CLS. You can say Python LLM sample.py. So I'm running this. Function is getting called. As you know, it will make use of the Olama model. It will take a couple of minutes. Since it's working on my local, that's why. As you can see, based upon the review, it classified the label as positive. So you see, it's able to do this because it's able to establish relationship between words. So what I want you to understand from this particular example is how powerful LLMs are and how LLMs internally are working. So we gave two examples to it as a reference in which one of the text was labeled positive, one of the text was labeled negative, and we gave a review ourselves. So internally what must be happening, the first text in which we had given label and the review, the first review would have been converted to a numerical representation, which is what we call as embedding or vector, correct? Same way, the second review would also been converted to a embedding or a vector representation, and the label will be associated with it. So when we gave our review, it will convert our review also to a numerical representation, compare it with both these ones, to which one it was more nearer, there it classified, correct? So this is how it was able to classify the label. It's a very classical example, a very good example to understand, correct? Yes. So where we made use of LLM models, and it also helps us understand what all LLM model can do, correct? It's a very classical LLM example. Similarly, we can also make use of LLM to actually perform calculations, correct? So here you can see the second example. So let me go up. So extend completion. You can see the parameters are nearly same. Olama.chat, content equals prompt, and temperature and number of predict, and we are getting the response, message, and the content, correct? So whatever response the Olama server gives back, we are taking that along with message and content. Okay, now here you can see we are defining a function chain of thought example, correct? And you are a helpful reasoning agent. Think step by step and provide answer. We are given the context. We are given a chain of thought, correct? And if two trains leave station 60 miles apart heading towards each other at this speed 20 mph and 30 mph, how long until they meet? This is a mathematical problem, correct? And we send it for completion. Now in this example, I also wanted to show you embedding. So we are getting the embedding of the text. You're able to see we have this function get embedding. So text model. Now the model which we normally use for embedding is nomic embed text. You can easily install it in our Olama. So it's supported in Olama. So as an example, yeah. So if you go and see here, you can run this command docker exec -it Olama pull nomic embed text. So if you do this, this will download this model. It's a very small model as compared to other models and will be easily available. The major use of this model is to convert normal text to embedded or vector representation, correct? Numerical representation. So you can see here def get embedding text model nomic embed text, and within Olama there is a function. Till now we use chat function. Here we are making use of embedding function, where we give the model and the prompt, and the result embedding we are printing, correct? Yes. So we also have this cosine similarity. I told you, once you convert a number, once you convert a text to a numerical representation, that is known as vector. To find relationship between two vectors or two text, you can use this cosine similarity. It makes use of a math module where it compares the value between this vector. Vector is collection of values. It's like an array, you can imagine, correct? So we are performing this dot product. If you remember, I told you it's a very important thing, dot product between the vectors, and correspondingly adding them and finding the square root and dividing them, correct? Yes. So it's a mathematical representation of cosine, where we do dot product of individual values and we take the square root and divide them, correct, correspondingly. And finally, we also have compare prompts. So in compare prompts, what we are doing, we are taking prompt A and prompt B, taking the test inputs, and in the results, we are comparing the text, input text which has been given, and we are seeing how much relationship they have, correct, and correspondingly completing both the send completions. We are calling send completions and check in how much relationship they are having. So this is what is known as chain of thought example. So when the chain of thought will get called, it will send this prompt, call it. Now embedding example will come in the next sample, but I just wanted to show you that we can also do embedding, correct? So in the chain of thought, what will happen? It will send this prompt to our Olama model and correspondingly get results, correct? We can get results from there. So let me go and run this. Sample 1.py. So in this sample 1.py, it goes to send completions. In send completions, it makes use of chat. Okay. But I just wanted to show you get embedding cosine similarity, how it looks. We will use this and compare prompts. This we will use in the next example. Just since it was written, I just wanted to show you here itself. So let's wait for chain of thought demo. It will take a couple of minutes, as you know, since it's working on my local. So it will execute and the result will come. Let's give another minute. You open one more command prompt and say docker ps docker logs. See, it's running. Yes, you see, it explains step by step. Are you able to see that? So instead of giving a single summarized output, here it's giving a more what we can say explanation oriented result. Correct? Train A is arriving at 20 mph, train B is traveling at 30 mph. Yes, so then logic, step by step. You see, step one, step two. Why it did step by step? Because we requested it in the prompt. If you go and see this at the top, you are a think step by step. You see, we gave that prompt. Change think step by step and provide the final answer. Since we gave this thing step by step, that's why it gave the results stepwise. Okay, so that is what we call as chain of thought. In chain of thought, instead of giving the output in one go, it will represent the step by step information about how it tackle that problem. Does it make sense, everyone? Yes. So this examples chain of thought explains how can we get a chain or step by step approach of what LLM taught to solve that problem. Correct. Now, along with that, we also learned about get embeddings. We did not use in this example though, but I talked about what is get embedding method. It gives the numerical representation of the text and cosine similarity, correct? Where I told you it gives similarity between two vectors and compare prompts, correct? So compare prompts will actually take prompt A, prompt B, and will also make use of test inputs and model and compare them, correct? So we will use it in the coming up example, which is here. So you see cosine similarity. Yes. Pick the one which is very similar, highest cosine similarity. So if you have two vectors which are very much related to each other, their cosine similarity will be very high. So the cosine similarity, cosine similarity actually is the angle difference between two vectors. And if two texts are very much related, their differences will be very low. Correct? So it's a vector. So two vectors, if they are related, vector is a directed line as per mathematics. So if you have two directed lines and the angle between them is very small, that means they are related. This is how it internally uses, correct? So what we do here is in cosine similarity, we try to find out the same method which we used. We find out whether there is relationship between two vectors, correct? Yes. So if this value cosine, if this value is very large, then there is no relationship, correct? So as an example here, you see, get embedding, I am calling king word. So it will give a numerical representation of that. Get embedding, it will take the king and queen and it will try to find the cosine similarity between them, correct? So if you go and run this, you will get a quite good value. You will get a value greater than 0.5, correct? Near about 0.8 you will get because there is relationship between king and queen. They are very much related to each other, correct? So even in the textual representation, they will be having a relationship. So the same code which we used like get embedding and cosine similarity, which I explained in the previous example, we are using it here. And we are comparing the prompts, correct? Embedded 1 and embedded 2. So let's try how this looks. So let me clear the screen. See, Python. See, the similarity value came out to be 0.74. So there is relationship, correct, between these two words. As I told you, anything greater than 0.5 is generally considered to be a positive relationship. Anything which is more nearer to positive 1 plus 1 means they have relationship, correct? The cosine similarity. Okay, so this is how internally LLM makes use of embedding and this cosine similarity to find out or predict the next word which it has to use, correct? So that's how it uses. Hopefully that makes clear. So when we do embedding, we convert that to a vector. So to establish relationship between two vectors, we can make use of this cosine similarity, correct? Yes. Highest cosine similarity. Okay. So this is how internally LLM makes use of this features. Hopefully that makes sense, everyone. I explained to you the logic of how it works. Now, so we did 3 examples, plain LLM. We also did LLM with chain, step-by-step approach. And finally, the third one, we also did an example on how does LLM internally decides whether particular textual information are related, correct? By using cosine similarity and embedding. So hopefully that gives you a clear picture of how LLM works. So going next, we will be talking about prompt engineering, correct? So in prompt engineering, core principles which we need to follow for any prompt engineering giving successful response is be explicit, specific and structured. If possible, provide few examples. Try to reduce ambiguity. Better to divide complex problems to steps and define the output format, in which output format you will like the output to be coming, correct? So these are the basic principles of prompt engineering. Always try to give as much details as possible so that the LLM doesn't have to assume anything and develop a solution. See, one of the things we have to always remember is that artificial intelligence is very powerful, but we have to give the contextual information properly if you want the response as per our expectations, correct? So that we have to be very clear, because from AI perspective, there can be many different ways of representing or giving a response, correct? So we have to be precise in self in indicating what type of output we are expecting, correct? Now try to avoid ambiguity. Ambiguity anywhere is a challenge. Same applies for AI. So try to give few examples. If you remember the one in which we did review and label, we were very clear in giving an example, correct? So reduce that ambiguity, give clear examples, break complex tasks into small tasks, correct? And define output format, in which output format you will like JSON, table, bullet and list. So basically prompt is a collection of instruction, context, input and output format. 4 things are required: instruction, context, input and output format, correct? So there are few prompt patterns, correct? So you can see zero shot prompting. You don't give any input. Summarize the paragraph below, correct? So that is what we call as zero shot prompting. Few shot prompting, you provide examples, correct? So you will say the example of review which we did, correct? Movie and review, that's an example of few shot prompting. Chain of thought, this also we saw. We tell the model to reason step by step, correct? So we saw the implementation of this in our Python code. And role prompting. In role prompting, you will say, so if you remember yesterday and all in the system, we used to say that you are a helpful virtual assistant. How will you respond? Same way, in role prompting, you can specify the role of the system to be a specific role using which it can perform this operation, correct? So you are a Java performance expert. So this is what we call as prompt patterns. So zero shot prompting means we don't give any input. Few shot prompting is we give samples. Chain of thought, we ask the model to represent the result step by step, and rule prompting. I think we have used all this in our examples. I covered few examples few minutes before. Hopefully that makes sense with this prompt patterns, correct? Now we also have a few advanced prompting techniques in which we have self consistency. So you generate multiple answers and choose based upon the best voting. We have a react pattern. This is very much used everywhere, especially in agentic AI. Reasoning and action selection, correct? So it will make use of reason, it will make an action and select the action. We also have meta prompting. So based upon the prompts, we will create more prompts to improve the results, correct? Prompting to improve prompts. Prompt chaining. In prompt chaining, we will break the workflow into multiple LLM calls, correct? And agentic AI. LLM calls tools, API doing reasoning. So these are the various advanced prompting techniques. Okay, so in agentic AI, we make use of external tools or API, correct? In prompt chaining, we break the workflow into multiple LLM calls. In meta prompting, we will prompt to improve the prompts. And in React pattern, we will use in reasoning and action selection, correct? So these are the advanced prompting techniques. So let's see each of them with an example. So self-consistency, the first ones, correct? So here in the prompt, we are saying a farmer has 17 sheep, all but 9 died. How many remain? Correct. So the LLM generates three reasoning path. You can see path A, it will analyze that first part. Path B, it will analyze the second part. Yes. This is known as self-consistent. So these are very much self-consistent way we should use whenever we have mathematical problems, logical puzzles, coding solutions. And it's used by agentic models, tools using LLM, retrieval based assistance. In all these cases, we prefer using self-consistency prompt, correct? Predominantly used for puzzles and mathematical questions, correct? Second is React pattern. So React pattern, we have a reason, we have act. This is used by agentic AI a lot. So, and it will keep on doing this, reason, act, and continue. So it will run this as a loop. So if you see the example task, find the weather in Bangalore and write a short summary. So reason number one, it will say I have to call the weather API. In weather API, I will pass the parameter as Bangalore. Whatever the API returns, that value I will capture and I will summarize, correct? So react. So reason and acting and continue, correct? This is the way we will do. Third is meta prompting. So in meta prompting, you will ask the prompt to improve your prompt to give better results, correct? So for example, the LLM improves your prompt instead of giving answers directly. So your prompt, fix my prompt, write code for chatbot. So now what meta prompt will do? It will make this prompt more specific, structured and goal focused. So you see, it will convert that single word, write code for chatbot, to something like write a Python chatbot using Flask that can answer FAQ. Yes. So this is a improvement of prompt, how to give prompt. So you can get better results from AI. That's what meta prompting sense. And prompt chaining. In prompt chaining, we will have multiple LLM calls, correct? Okay, so for example, summarize a PDF. So summarize a PDF means first we will have to read the PDF. From the PDF, we will have to capture the important points. We will have to summarize that points and generate a cues from that. That's also asked, correct? So we'll have to generate cues from the summary. So here we make use of something known as retrieval augmented generation system, RAG, which we look that into details in few minutes. So we make use of RAG systems, workflow, multi-step analytics. All these places prompt chaining will be used. Okay. And last one is the tool use, which is used in agentic AI. Correct. So this again makes use of API and external tools. So external tools can be either API, it can be CRM, it can be database. It will compare and give you the results. Correct. So flight underscore API dot search. Mumbai and Delhi tomorrow. From Mumbai to Delhi tomorrow. Correct. So these are again used by AI agents, automation, data lookups, API orchestration. All these places tool use is used. Okay. So this is how this prompt engineering patterns are there. Correct. So yes. So these are the patterns implementation with respect to Olama and Python. Correct. So self consistency. So here we are making use of the request and JSON module. Request is a module which is used in Python to actually make REST API call. So you can call API and get the result. For that, we are using this. And Olama URL. I told you yesterday itself that when we use Olama as a support for API, REST API, you can request that REST API and it can give a response. Model you see, I am using Llama 3. So in Olama chat function, it will take a prompt, fire, and whatever result it comes, that result it will convert to JSON and capture the response. Correct. So the first example which we are going to do is self consistency. So if you remember, self consistency we covered. It's the first example. Correct. A farmer has 17 sheep, all but 9 die. How many remain? Correct. So it makes use of reasoning paths. So let's try that. So if you come here, so in self consistency prompt and samples we give. So for how many samples we give, we call this Olama with prompt, and whatever results it gives, that results we capture. Then by using collections, we make use of a counter of answer and select the answer which is most common. So this counter comes from collection which takes all this list of answer and which answer is occurring more number of times, that answer I am selecting. Correct. You can see consensus, counter dot most common one, and that one is what we use as the answer. Correct. So a farmer has 17 sheep, all but 9 die. How many are left? So we are passing this as a prompt to self consistency. So let's see how this works. So this is within patterns. So we'll do CLS CD patterns. Okay, so if I go here and say Python self consistency.py. Let's run that. Again, it will take 1 or 2 minutes. The reason you already know, it's running on my local system, so it will be slightly slow. Let's see the output. While it runs, also go and check the Olama model. See, it's still processing. Everyone able to see? So if you see the logs of the Docker, it will show you all the steps which are run. Wait here, output will come. So this is how we are implementing the various prompt engineering patterns in Python. Yes, making use of Olama and the request module as well as the supporting JSON module. All these three things we are using. So this is a code implementation. So we did samples 5. So based upon 5 output, it will compare the output which is occurring maximum number of times, that it will give us the answer. Let's give it a minute. You can see it gave the answer. Along with that, it also explained. It explained everything in steps, correct? So as you can see, this is very much useful for students, correct? Who can understand what it does and how it works, correct? Which is the correct answer. So self-consistency example we did. So what we learned in this example, we learned that self-consistency one makes use of consensus, correct? So it runs the same problem n number of times and selects the best one and gives that as the answer, correct? This collections.counter, it's an inbuilt class which is available in Python in the collections package, and most common is their function, correct? Which we used. So we also printed all answers. So you can see all answers. It started one, clever one. So all the answers it printed, clever two. You're able to see. So all that things are there, and the final answer which it selected, it gave as the answer, consensus answer. If you see, so out of all the answers, one of the answers was selected as consensus answer. Correct. So that answer is what it printed. With me, everyone. So in this example, we learned about self-consistency. Correct. Same way, the second pattern. So I also showed you how to ensure self-consistency from normal prompt, and also how to use it within Python code. Correct. Next is the React pattern. So let's try that. Go here. So this is the React pattern. Again, we are using the Olama URL and model. The Olama chat function remains same. We have the prompt with model, prompt, and stream equals false. We don't want stream, we want the result, and we make use of request.post. So here we have a calculator. Now the calculator will take an expression and evaluate the expression. Now we have this React function which takes a prompt. So you see, you are using React, think step by step and decide on the action. Available tools are calculator. So this calculator function is available in which you can pass the expression, correct? And taught is tool and input, correct? So whatever input user gives, that input will be taken to tool. Now what we are doing here is olama.chat reasoning prompt. So whatever reasoning prompt we had, that we are passing along with the actual prompt given by the user, which we say as user query. And then we extract the action, correct? So we extract the action from where? We extract the action from TOTS. So RE stands for regular expression module. It's an inbuilt module available in Python. So using which we check whether the action is present or not, correct? What action the user expects. And wherever the action matches, we are making use of groups. So if you see here, action colon tool and input is what we are doing, correct? So here input will become match.group 2 and tool will become match.group 1. So this match.group 1 will give the first matching pattern and match.group 2 will give the second matching pattern. As you can see, there are two patterns here, correct? You can see tool That is the first pattern. And this square bracket and input, that's the second pattern. That's what we wrote here, correct? Anything within square bracket, that is my input. Whatever is present before that, that is my tool, correct? So we are taking the tool. If the tool is calculator, we are calling calculator with our input. So it will eval. So that eval function will evaluate it and give the results, correct? And final observation back to LLM. You previously said this. Observation from tool is this. Give final answer now. So you see, you're calling the model multiple times, correct? Based upon your observations. And then you get the final answer. The final answer which you will get will be very much tuned, correct? So this is how we are using. So we are expecting the input to be in particular format, and we will represent the output, correct? For example, what is 234 star 89? So 234 star 89, correct? So when this will get passed, now let's see, when we call React, let's scroll up. So this is the React method. It will take that what is 234 into whatever 49 it was. So this will pass that prompt user query here along with reasoning here, correct? So the reasoning action colon tool. So what a tool colon input. This is what we expect as the response, correct? So whatever input it will give, it will go and check. So it should give the calculator as an output, and this within the square bracket, what is that? 234 and 89 as the input along with star, correct? So then what we are doing is we are searching the output given by this first chat to see what is the calculator and what is the action, and then we correspondingly call it, correct? So let's see how this works. So in this case, and after getting that result, we are again formatting the result in the final prompt, correct? So if I run this, so React, as you know, it will reason and then action, correct? So let's run this. Python React.py. Run this. Again, it will take a minute. You know, it has to call Olama 3 times, correct? In this example, so it will take a minute. See, action came, calculator 234 into 89. Everyone able to see that? Hello? So LLM talks production thought I need to calculate the product of 239 and 89. And action is calculated 234 into star 89. Everyone able to see that? It gave the input clearly. We can handle here in the calculator. We can say that it should be 234. What will be the output of 234 into 4? Again, we'll have to create one more call. But as you can see, the LLM thoughts are very clear, correct? Product of 234 and 89. Action calculated 234 and 89. So it's calling the calculator function with 234 and 89. Does it make sense, everyone? So when you call React, it gave you the final answer again. So it called the React, it called all these functions. Okay. The only thing which happened wrong here was final. Let's just move this inside. This formatting slightly became like this. So this is the format. Final answer, final prompt. Okay, that sounds good. Okay, so this is how we can use. Hopefully that makes sense. It gave the action, it gave the calculator. Let me try running again. Go back, say CLS. See, it gave clearly action calculator 234 start 89, correct? Hopefully that makes sense, everyone. So it creates a call, use the call, generates the output, finds the pattern, and decides the output, correct? LLM thoughts plus action, if you see. If you compare here the LLM talks, I thought I need to calculate the product of 234 and 89. Then we printed the action, correct? Yes, so we printed the action. Whatever action came, we make use of re.search and we captured the tool and tool correspondingly. So that will get printed tool output. And so it gave the action as you can see here, this thoughts which we printed here were the original thoughts. And then we printed the action, correct? So if you go and see the output, action calculator 234 star 39. So if you come here, it printed the corresponding action and then it printed this. We could have also printed the tool if you want. Print tool, comma tool. Let's print tool input, comma tool input. So let's run again just to check it's working. Yes. City. You can see a tool came as calculator and two input came as 234 star 89 and you see the total output also came. You're able to see that everyone? So total output came as this. So tool input, it went to calculator. It called this calculator function. So when it called the calculator function, it correspondingly calculated that eval and that result got printed, correct? Tool output. And now the remaining part of final prompt is also running. See, according to my previous thoughts, 234 into 89, the result was observed to be 2. The final answer is 20826. So this further improved the answer, correct? You're even able to see that it further improved the answer and gave the improved answer to us, final answer to us. Hopefully that makes sense. So there was few intent problems which we resolved. So you can see when it calls. So what is the takeaway from this example? And the takeaway from this example is, in this example, we are given few mathematical calculations. We are able to use model to understand that or to reformat that question into a format of action followed by tools followed by input. So the tool which we got was calculator and the input which we got was the input values which were entered by the user. And then we call the corresponding helper method which will evaluate that result, and that result is what we are using and we are formatting the output, correct? So we can also use, so what this example shows is we can also use a model to reformat our query into a format which is expected by the second tool, correct? So reformatting of tool is also possible in prompt engineering, which is what we got in a React example, correct? So same thing we explained here in the PPT. See, find the weather in Bangalore. So it has to call the Bangalore with location. So from this sentence, it should be able to find Bangalore is the word of interest and then call the API and get the result and again summarize it in a form which is much easier to understand, correct? Don't you think we implemented the same thing with our example, correct? So this is the second prompt pattern, React. Now we can go for the third one. So third one was, go here, meta prompting, correct? So let's see meta prompting. The example which we consider here was write a code for chatbot, correct? And it gave you more specific instructions. So let's see how can we implement meta prompting. So again, we are using the same Olama chat function, which will make a REST request call, post call to our Olama URL and JSON data. Now in the improve prompt, we are making use of meta prompt and we are given the roles very clearly. You are a prompt engineering assistant. Improve the user prompt by making it clearer, more detailed, with constraints and with better structure, correct? So the user will give bad prompt. So whatever user gives us input, we consider it as bad prompt and we will improve it, correct? By using Olama chat meta prompt. And since we have already given the metadata information like what we expect, it will give us the improved response, correct? So if I call this improve prompt, write a code for chatbot. So let's try that example. So this is the implementation in Python. So if I go and call the meta prompt in, so we have set what we are expecting. We expect our prompt to be polished in such a way that it can represent or result in a better prompt, which can be given to any AI tools, which can understand and give the result, correct? So that's what meta prompting is trying to do. Let's wait for a minute to show the output. While this is running, we can also go and see our Docker logs. Yes. See, it's still running. So if you go to the Olama logs, it will start showing how the model is running and all, correct? That's why I'm in every example, I'm just showing you how to go and see the Olama logs. The same example which was listed in the slide, we are using, correct? Let's see what output it gives. Then we'll go for prompt change. See, the corresponding output of the prompt is shown. See, it converted that single prompt to so big. Develop a conversational AI chat bot that can engage in natural language conversation with users. The chatbot should be able to understand and respond to basic inquiry provided information, even offer suggestions, recommendations, constraints, language support, domain expertise. See, this gives further advice to the person who actually wants to give the prompt, correct? The person who is actually given prompt but now not thought about these constraints. Now, when that person sees what all constraints can be imposed on a chatbot, he or she can correspondingly fill the details and make it more good, correct? So that's the advantage of this meta prompt. It will give you more information which you might have ignored or skipped, which you can give as input to make your solution more better, correct? So you can see that. Now next is prompt chaining. So in prompt chaining, summarize PDF and generate quiz questions, correct? So of course we are not going to read from PDF, but we'll emulate something like reading from PDF by giving some input, correct? So here we have multiple LLM calls. So let's go and see that. Prompt chaining. So again we have Olama chat, the same function which we used earlier. Then we have chain summarize. So summarize the following text in 5 bullet points. So we will give a text. It will summarize that text into 5 bullet points and it will give me the output. This is in chain summarize. And in chain generate quiz, it will take a summary and generate 5 quiz questions, correct? So the text which I gave is large language models are deep neural networks trained on large corpora of data, of text. This is what we give as input. So first I call the chain summarize method, which will generate a 5-pointer bullet points of this particular text. And using that text, which comes as result, we will generate quiz questions, correct? 5 MCQs. And then we will do the summary. I'm printing the summary also, and I'm also going to print the quiz questions. So this is prompt chaining where we have output of one prompt serving as input to other prompt, correct? See, output of first prompt is serving as input to second prompt. That's why this is known as prompt chaining. There is a chain. So let's try running this. Python prompt chaining.py. Since there are two calls, it might take a minute. Let's just wait here till the response comes. And when it runs, it will give you the corresponding output. So once this runs, it will give me the output. So the output of the first prompt will be taken as input to the second. So we'll also check. This is also working. So output should come. So here we can also extract the data from some external sources like PDF documents and all. How to do that, of course, I will teach you in coming up sessions. We'll have to make use of some libraries which does that, correct? Yes. We'll cover in that in the later part of the session. And I think after this the Agentic AI, which will get data from API, search and give me the result, correct? So we'll be doing that after this. So not only did we learn prompt engineering from the perspective of how to do it, but we also learned how to implement it, which is what makes this very unique. We implemented all the patterns of prompt engineering, correct? And learned in detail how to implement each of them using models, correct? See, so you can see it generated MCQs and the summary both. If you scroll up, it generated the summary of large language models. Here is the summary. You can see deep neural networks, LLMs are trained. This training enables models to learn. And then we also had quiz questions, and we have 5 quiz questions with options and the correct answer, correct? So it becomes so easy for anyone to use this prompt chaining to generate output as per choice based upon the input, correct? So now we are left with this agentic AI tool use. Tool use means we are going to make use of external tools like API. Now, as of today, we will be using only a emulated method or a mocked method, correct? In coming up sessions, we will see how to call an API. So here we again make use of the same Olama chat method. We have this get weather method. This get weather method is supposed to expose itself as an API or a tool from where we can fetch the data. For now, I have given fake data such as Bangalore is 28-degree cloudy, Mumbai is 32-degree humid, and Delhi is 26-degree clear skies, correct? So based upon the city, we will get the data or we will get no data. Now we have this agent weather in which we have the query. So here we are saying you are an agent with access to weather city. If user asks for weather, respond action equals weather city, else say action none, and whatever query comes, that query will come, correct? So if you see in the Olama chart, whatever user gave as a query has been embedded within this React prompt. Again, we are making use of action, same like what we did in our couple of meta prompting example, correct? Same way. So we make use of action. Sorry, in the react.py, same way. So we parse it, we take the weather, we get the weather with the argument, and in the final prompt, we give the observation, correct? So agent, what is the weather of Bangalore? So it will go here, find Bangalore as the city, will make that query, find the action as calculate the weather of Bangalore, get the weather from this particular function, and finally give in the result. Okay, so let's run this. So this also looks very interesting because it's getting data from somewhere else, correct? Some other system. In our case, from mock data only, but in real world, it will come from some APIs or tool. Yes, so tool use .py. So you can see React and this tool use, these patterns slightly overlap because both of them are used by agentic AI, correct? So you see the tool use, it went from weather Bangalore. Now it will try to get the data from our function and show the result. Yes. The current weather in Bangalore is 20-degree with cloudy skies. You're able to see that, everyone? So here so again, here also we made use of two Olama chat. But unlike the earlier one, we directly did not give the output, correct? We further process the output to generate more inputs, which can be then fed as input, correct? So that's how the tool use pattern works. It's nearly same as React pattern. The only difference is in more or less the data in tool use can come from multiple sources like API, database, files, tools, and so on. while in React predominantly it's API, correct? So we have seen all these different patterns and their corresponding Python implementations, correct? So generally the output of LLMs are based upon or evaluated on multiple factors, accuracy and consistency being the most important factor along with safety, quality dimensions, relevance and so on, correct? The methods are human evaluation. We also have A/B test. One of the A/B tests which we did was in the comparison, correct? Reference model test and model based evaluators are there. We will use one more LLM as a judge, correct? Which will compare the output and give which LLM performed the best. Now, one of the important things is hallucinations. So, what is hallucinations? Hallucinations are, if you remember in one of our calls when we made to Alama, we gave temperature, correct? So, in temperature, 0 means factual, greater than 1 means it can be creative or imaginary, correct? So, sometimes AI can generate some hallucination data or hallucination response, a response which is not expected. So, if you don't want hallucination to happen, what we will have to do is, along with all the models, we will also have to give a set of data from which a result can be picked off, correct? So when you give the context, you will, along with giving the context, you also give the system in which you have to look up to get the data. Now, for example, I will give you a case of hallucination. Imagine you created a agentic AI solution for a customer. The customer comes and says, hey, I want to know my balance for this account. Okay, very straightforward question. Now, if you have not set the context in agentic AI, it will go and check internet, and as a result, it can give result which is not related at all to the use case of the user. Correct? It might return a result saying how to check your balance in some ABC bank. Correct? So one of the use cases which generally happened here is customer care number. Correct? So what is your customer care number? If you go and check internet, you might get customer numbers from n number of websites, and any of that customer number can be given as response, correct? Which will totally kill the purpose. This is an example of hallucination where the data is not restricted. The data is not coming from a set. Now, this is very important for use cases like finance, where the result is supposed to be very much accurate. So, to solve such hallucination problems, we make use of RAG. We also add validation rules, and we try to avoid open-ended generative prompt questions, correct? So, one of the best way of handling is by using retrieval augmented generation. So we will just get introduced to it today. We will learn a lot about it in coming up sessions. So what happens in retrieval augmented generation is, when the user query comes, we will embed the query and we will search for that query in relevant documents, correct? So here when we say relevant documents, it can be physical documents. Physical means PDF or digital documents like PDF, Word, or it can also be a database, correct? So the LLM then constructs the context based upon the response which it gets from this lookup, and it makes its results based upon that, correct? So the advantage here is you are restricting the result to a particular domain, to a particular data set, correct? So you are using the LLM benefits, but you are restricting the question to a particular data set from which the result will be captured, correct? So that will result in more precise solution to the user rather than giving them any solution from internet which may not serve their purpose, correct? So you see the benefits are lower hallucinations, domain specific accuracy and updatable knowledge. So how can we do this is what we will see in coming up sessions, correct? RAG is a big topic. So I just introduce you to RAG. So in RAG, it makes use of LLM, but the data from where it will come is from a proper data source. correct, which the organization is maintaining. So what are the key takeaways today? We understood LLMs. We understood how LLMs work internally. We learned what is embedding. Embedding is conversion of textual data to vectorized format, correct? We also learned how LLM works in terms of cosine similarity, how it finds out similarity between two words, correct? By using embedding and vector calculations. We also learned various patterns with respect to LLM, correct? If you remember LLM sample 1, sample 2, chain of responsibilities, all that patterns we learned. Then we slowly went and learned about prompts. We learned about prompts patterns, correct? Different patterns which can be applied. We learned from self consistency all the way till tool use and implemented each of them, correct? And we also got introduced ourselves to RAG, correct? Now we will cover few interview questions which are generally asked. So explain the retrieval augmented generation pattern and how it is typically implemented in Python and what problem does it solve. Implementation in Python, of course, we will see in future. But what problem it solves, I just explained to you a few minutes before. One of the major problems faced by AI or agentic AI solutions is hallucinations. Hallucinations means getting a result from internet which may not solve the purpose, correct? So that can be solved by using RAG. So the answer is RAG is an LLM application pattern which combines an LLM generative ability with an external knowledge base, correct? To produce more accurate, more grounded and context aware responses. This is very important. It generates response which actually matters, correct? Rather than giving any response. In the same way, the second question, this second question is also a very interesting question. We know that transformer is the foundation of LLM. So what is the fundamental mechanism that allows it to capture long range of dependencies in text and how it is calculated, correct? So I told you it makes use of embedding, correct? Transformer makes use of embedding. So using embedding, it calculates the vector representation. Then using cosine similarity, it will try to find out the similarity. So cosine similarity internally makes use of vector calculations, correct? And using that vector calculation, it will be able to establish the relationship between two different words. So that is what the expected answer. So you see the fundamental mechanism which transformers use is known as self-attention mechanism, correct? I told you attention means specifically focus on words which are of significance, and it makes use of that words, and after embedding it will take each of that words and give importance to that words, correct? So you see in the mechanism in the key vectors for each token the model generates three vectors: query, what I am looking for; key, what I can offer; and value, the content I can provide, correct? And it makes use of a function with name softmax, where if you see the top qk, that is used to calculate the relevance score, correct? How much your predicted output is matching with the output which was expected, correct? And it uses that to gain attention weight, and based upon that it captures the output. So you may not remember this formula, but the mechanism it uses, the self attention mechanism, and the importance of each and every word token is very significant, correct? So these are the interview questions which we wanted to cover. Hopefully you all enjoyed the session. We covered a lot today in terms of prompt engineering and prompt engineering and LLM. Hopefully the fundamental building blocks of LLM and what type of problem it solves is very much clear to everyone. Thank you everyone for your time. Appreciate your patience. We will again catch up tomorrow to learn something new. Thank you.